Alright, we're going to continue one more day of Extrema on the interval, and the first things I'm going to look at is just some graphs again. And what I'm asking you guys to do on these is just to determine from the graph whether I have a minimum on the open interval A. And we're only going to look for if it has a minimum. So does graph have a minimum on open interval A to B. So let's look at each one of these separately. On the first one, does A have a minimum value, or on this first one, does this graph have a minimum value? Well, it looks like down here, if I was going to have a minimum value, it would be right here. But since it's an open dot, this one does not have a minimum. Now let's look at that just a little bit different. This is the same graph, but as I get close down here, this does have a minimum right here. This does have a minimum. This would be its smallest value. Back on the other one, it didn't have a minimum because that was an open dot on its smallest value. Now on this next graph, if you look here, the minimum would occur here at B, but since it's an open dot, it does not have a minimum. And then over here at this one, looks like the minimum would be down here at B, but since there's not a closed-in dot, there can't be the minimum there. But there is a minimum. It is right here. So it's not at B. It's somewhere between A and B, but there is a minimum here. So this one does have a minimum. Now this next problem may be a continuation of the problem through 2 videos, but I'll go ahead and get started on this one. This is a little bit longer problem, at least to explain. The formula for power output, P of a battery, is given by this equation. So I'm going to go ahead and write that equation right here. And we're going to fill in what known values are given to us as we read them. It then goes on to say, where V is the electromotive force in volts, and R is the resistance. I is the current. We're supposed to find the current. So that means we're going to be solving for I's. That corresponds to a maximum value. That tells me I'm going to be taking the derivative with respect to I of P in a battery for which V is equal to 12. So they're telling me that V is 12. So I'm going to go ahead and put 12 in there. And that R is 0.5. So I'm going to put 0.5 in there. Remember, I'm solving for I, so I know that I's are going to be my variables. It then goes on to say, assume that a 15 amp fuse bounds the output in the interval 0 to 15. So I'm talking about a closed interval from 0 to 15. And then it asks me another question. We'll go back to that question in a little while. What it's asking me to do is find the maximum value. So that means I'm going to be taking the derivative. So I get 12 minus, well, 0.5 times 2 is 1. So I just get I and lower that by 1, it gives me 1. So where is my derivative equal to 0? There are no places where the derivative does not exist. The derivative equals 0 when I is 12. Remember, I is the current. So when I is 12, I need to check that value. I'm going to check what the value of P is when I is 0, when I is 12, and when I is 15. Now, where did I get these other values? Well, this is an endpoint. This is my critical number. And this is my other endpoint. I will continue this in the next video. Alright, this is a continuation of the problem from the prior video. And what we were getting ready to do is we were finding the current that corresponds to the maximum value of P. So I'm looking for the maximum at which this would occur. What we're going to do is we're going to take this, we have our critical numbers, and we're going to test each one of those back into this original problem. Well, on this one, I know that my I When my I is 0, my P is 0 when I plug those in. When my I is 12, well, I have 12 times 12 minus 0.5, 12 squared. That'd be 144 minus, this would end up being 72. So that would be 72. And this last one, when I plug in 15, I'd have 12 times 15 minus 0.5, 15 squared. That does total out to be 67.5. So the maximum would be at 12 when I is 12. So max when I equals 12. Now there's one more question to this, and it says, could the power output be increased by replacing the 15 amp fuse with a 20 amp fuse? And what we're going to do is just talk about this a little bit. In this graph, I can see that it increased from 0 to 72, but we determined this to be its maximum. So what's going on now is that it's decreasing. So that means that if I was 20, okay, if I was 20, that would not make any difference because P is decreasing once I is 12. So we're going to write that. No, a 20 amp would not increase power because P is decreasing for anything where I is greater than 12. Okay, my last example is just an example to help explain critical numbers of something maybe that's a little bit harder. So we're going to do this derivative, and what makes this difficult is just the product rule within the quotient rule and then trying to factor some things out. So I want to show you an example like this. So we're going to find the first derivative of the derivative of the second. The derivative of the second would be 3x plus 2, lower it by 1, take the derivative of that part right there, which would be a 1, plus the second times the derivative of the first, which would be 2x minus 4, take that derivative, which would be a 1. So what can we do to simplify this? Well, really, if I look at this a little bit closer, I'll notice that there is an x minus 4 in each of these. There's an x minus 4 actually factored out. These are all being multiplied together, and so are these. So I could take out the x minus 4, and then if I look a little bit closer, there's x plus 2's in each one of them. There happens to be at least 2 of them. So I could take out an x plus 2 squared. Now I'm going to make brackets here so you can see that what I'm doing is really factoring those things out. So from this first term, I factored out an x minus 4, but there's still another x minus 4 left. And there's also the 3. But I've taken care of the x plus 2 squared because I have factored that out. Then I'll bring down my plus sign. Notice I've already taken out the x minus 4, but I need the 2, and then I need the x plus 2. And I need another, just one of those because I've taken out 2 of them already. What does this do? Well, it means that I have critical numbers. I can see the first 2 rather easily. I have critical numbers at x equals 4 and x equals negative 2. This one I'm going to have to solve just a little bit. So I've got 3x minus 12 plus 2x plus 4. Combine my like terms. That gives me 5x minus 8. So there's another critical number right here at 8/5. So this was just a little bit harder problem on finding critical numbers where we might need to factor out some things. Otherwise, it makes it pretty difficult to find those critical numbers.